It's quiet now, isn't it? The sounds of the day, the rush and the noise have finally faded away. Maybe you are sitting by a window, or perhaps you're just closing your eyes, picturing it in your mind, the night sky. Take a breath, a slow deep breath in, and then let it out. Feel the stillness settle around you. When we look up into that deep dark expanse, it feels personal, it feels like it belongs to you. You see the first few pinpricks of light, one star then another, then countless more. There is a sense of calm, but also a sense of curiosity, a feeling of how incredibly large everything is. We are here on the surface of this small blue-green planet looking up into an ocean of darkness that stretches on forever. It makes you feel small, but not in a bad way. It makes you feel quiet, connected. You are looking at the same stars that your ancestors looked at, wondering the same things. Tonight we are going on a journey together. This isn't a race. We are not trying to get to a destination quickly. We are not here for speed. We are here for contemplation. This is a slow walk, a quiet drift. We are here to think, to wonder, and to feel. We will spend a little time exploring what we know. We know that those lights are stars, massive suns, burning gases like hydrogen and helium millions and millions of miles away. We know our planet is spinning orbiting one of those stars. We know there are other planets, giant worlds of gas and small worlds of rock. We know there are galaxies, huge spinning cities of stars. But more importantly, this journey is about what we don't know, and that is where the true wonder begins. We spend our days needing solid answers, facts and solutions, but the night sky invites us to be comfortable with mystery. It asks us to simply look without needing to explain everything. The universe is mostly empty space filled with things we can't see, things we have only just given names to, like dark matter and dark energy. We are only just beginning to understand. This is a monologue for you. It is meant to help you relax. It is a space to reflect, to let the edges of your day soften and blur. As we look out into the cosmos, we're really just trying to find our place in this grand silent picture before we fall asleep. We are a part of this. You are a part of this. And tonight we are just going to float in that knowledge peacefully. Look up at the night sky. What do you see? If you're away from the city, you see a spectacular tapestry of stars, planets, and perhaps the faint milky smear of our own galaxy. Between these points of light, there is space. We call it empty space. It is black cold and appears to be an abyss of near total nothingness. This has been our assumption for millennia, that the universe is comprised of the things we can see, the stuff, and the vast empty void that separates them. This assumption is wrong. In fact, it is the most profoundly wrong assumption we have ever made about reality. When astronomers and physicists began to carefully measure the universe, they ran into a problem. Their numbers did not add up. The equations that perfectly describe gravity here on Earth, the laws that keep our feet on the ground, and the moon tethered to our planet failed spectacularly when applied to the grand scale of the cosmos. The universe they discovered is behaving as if it's filled with an enormous amount of stuff that we cannot see, touch, or detect in any conventional way. This is the great mystery of our time. All the stars you see, all the gas, all the dust, every planet, every person, every black hole, all the normal matter that we understand makes up less than 5% of the total universe. The rest is missing. The vast majority of the cosmos is an invisible enigma. This missing component, which outweighs all the atoms in the universe by a factor of more than 5 to 1, is known as dark matter. It is crucial to understand what dark matter is not. The name is misleading. It is not dark in the way a cloud of black dust is dark, which would block the light from stars behind it. It is not a collection of burnt-out stars or cold gas. Dark matter is not dark. It is invisible. It is perfectly, completely transparent. Light passes through it as if it is not there at all. It does not interact with light, magnetism, friction, or any of the forces that shape our daily lives. Imagine a ghost walking through a wall. The ghost and the wall do not interact. Now imagine that the entire universe is built from an invisible ghostly substance, and the normal matter we are made of is just a tiny, insignificant bit of debris floating within it. The only way we know this ghost is there is through its gravity. Dark matter has mass, and its mass exerts a gravitational pull. It is the invisible puppeteer of the cosmos, and its strings are pulling on everything we can see. We cannot see the puppeteer, but we can see the puppets, the stars, the light, the galaxies dancing to its tune. The story of dark matter is the story of astronomers observing this impossible dance and realizing with a chilling sense of awe that something else must be leading. The evidence for this invisible substance is not found in one obscure corner of physics. It is everywhere we look. The clues are overwhelming, etched into the very motion of the stars, the shape of light, and the grand architecture of the universe itself. The first and perhaps most famous clue came from the stubborn observations of an astronomer named Vera Rubin. In the 1970s, Rubin was studying the rotation of galaxies, starting with our neighbour Andromeda. Our understanding of gravity based on Newton's laws makes a clear prediction. Stars at the edge of a galaxy, far from the bright dense centre, should be moving much more slowly than stars near the middle. In our own solar system, this is exactly what happens. Mercury, close to the Sun's massive gravity, whips around at immense speed, while distant Pluto plods along in its orbit. Vera Rubin expected to see the same thing in Andromeda. She measured the speeds of stars and gas clouds at different distances from the galactic centre. What she found was impossible. The stars at the very edge of the galaxy, far out in the dim periphery, were moving just as fast as the stars near the core. This finding was revolutionary and at first dismissed. It was as if she had observed Pluto orbiting the Sun at the same speed as Mercury. There was only one way this could be possible. The galaxy had to be much, much heavier than it looked. The visible stars and gas were not enough to provide the gravitational glue needed to hold those fast-moving outer stars. To keep them from being flung off into the void, there had to be an enormous invisible halo of matter surrounding the entire galaxy, exerting its gravitational pull. Rubin had found the ghost's footprint. Her data showed that this invisible halo was not a minor correction. It contained at least 5 to 10 times more mass than the entire visible galaxy combined. This galaxy rotation curve problem has been confirmed in virtually every galaxy we have measured since. The second line of evidence comes from the universe's ability to act as a lens. Albert Einstein's theory of general relativity tells us that mass warps the fabric of spacetime, and light, as it travels through space, must follow these warps. A massive object like a galaxy cluster will bend the light of any object located behind it, much like a glass lens focuses light. This phenomenon is called gravitational lensing. When astronomers look at massive clusters of galaxies, they see this effect in action. The light from distant background galaxies is distorted, stretched and magnified into beautiful arcs and smears of light. We can use these distortions to perform a simple cosmic calculation. We can count the visible galaxies in the cluster and estimate their total mass, and then we can calculate how much mass would be required to bend the background light to the degree we observe. Every time the numbers are wildly different. The observed bending of light is far, far stronger than the visible mass can account for. The lens is much heavier than it appears. Again, the conclusion is inescapable. These galaxy clusters are swimming in a colossal invisible sea of dark matter. Its gravity is what truly bends the light. We are in effect weighing the invisible, but the evidence does not stop at individual galaxies or clusters. It extends to the largest structures in existence. If you map the locations of millions of galaxies, you find they are not distributed randomly. They are arranged in a vast interconnected structure of filaments, nodes and walls separated by truly enormous empty voids. This is known as the cosmic web. It is the scaffolding of the universe. Computer simulations that try to recreate the universe's evolution cannot produce this web-like structure only using normal matter. The universe is 13.8 billion years old. In that time, the weak gravity of normal matter alone is not strong enough to have pulled itself together into such an immense and complex structure. However, if you add dark matter to the simulation, a cold invisible substance that does not interact with pressure or light, it all falls into place. In the early universe, this invisible scaffolding collapsed, first forming a gravity well, or a gravity riverbed. The normal matter, the gas and dust, then simply fell into this pre-existing dark matter framework like water flowing into a riverbed, where it clumped together to form the stars and galaxies we see today. The galaxies exist where they do because the dark matter told them where to go. Finally, there is the most profound clue of all the echo of the Big Bang. This is the cosmic microwave background, or CMB. It is the baby picture of the universe, a snapshot of the oldest light released when the cosmos was only 380,000 years old. This light is incredibly uniform, but space-based telescopes like the Planck satellite have mapped tiny, subtle ripples or variations in its temperature. These ripples are the seeds of altered core structure. They are the initial quantum fluctuations that eventually grew into the cosmic web. The exact size and pattern of these ripples are a perfect diagnostic tool. They tell us with stunning precision what the ingredients of the early universe were, and the data is crystal clear. The baby picture of the universe only makes sense if it was composed of roughly 5% normal matter, 27% dark matter, and 68% dark energy, a different but related mystery. The cosmic microwave background is the smoking gun signature of dark matter left behind from the dawn of time. The evidence is settled, the footprints are everywhere. We live in a universe dominated by an invisible ghost. The next logical question is, what is it? What is this ghost particle? For decades, the hunt for the identity of dark matter has consumed thousands of scientists, and the list of suspects is both creative and bizarre. The leading candidate for a long time was a particle known as a WIMP, which stands for Weakly Interacting Massive Particle. This was a beautiful theoretical idea. WIMPs are hypothetical particles that are massive, perhaps 100 times heavier than a proton, and weakly interacting. This means they do not feel the electromagnetic force, which is why they are invisible, or the strong nuclear force which holds atoms together, but they do feel the weak nuclear force responsible for some forms of radioactive decay and gravity. This weakly interacting part is key. It means that while trillions of WIMPs might be streaming through your body and the entire Earth every single second, one of them might, on a very, very rare occasion, bump into the nucleus of one of your atoms. What made WIMP so compelling was something called the WIMP miracle. Physicists working on completely different theories like supersymmetry, which posits that every known particle has a superpartner, independently predicted the existence of a particle with the exact properties of a WIMP. Furthermore, they calculated that if such a particle existed, it would have been produced in the Big Bang in exactly the right quantity to account for all the dark matter we observe today. It seemed too perfect to be wrong. Of course, before scientists hunted for exotic new particles, they checked for more boring culprits. They searched for machos, or massive astrophysical compact halo objects. This is a catch-all term for normal stuff that is just dark and hard to see. This includes cold burnt-out stars, white dwarfs, neutron stars, planets that are not attached to a star rogue planets, and perhaps millions of small primordial black holes. Scientists hunted for machos by staring at millions of stars, looking for an effect called microlensing. If a macho passed in front of a distant star, its gravity would briefly act as a lens and make the star appear to brighten. They did find some of these events confirming that such objects exist, but they did not find nearly enough. The number of machos they detected can only account for a tiny fraction of the missing mass. The conclusion was clear: dark matter is not made of normal stuff that is just hiding. It must be something new, something truly exotic. As the hunt for WIMPs has continued without success, other candidates have risen in prominence. The most popular alternative today is a ghostly, almost massless particle called the axion. Axions are the opposite of WIMPs. They are not heavy but unbelievably light. But according to theory, they would have been produced in the Big Bang in immense quantities, trillions upon trillions in every cubic centimetre of space, forming a vast cold sea of particles that collectively has enough mass to be the dark matter. Axions were not invented to solve the dark matter problem. Like WIMPs, they were first proposed to solve a completely different thorny problem in particle physics related to the strong nuclear force. The fact that they also happen to be a perfect dark matter candidate makes them extremely compelling. And what if dark matter is not just one thing? Some theories propose a dark sector, or a hidden valley. This is the idea that dark matter may not be a single lonely particle. It might be a whole family of particles with its own set of dark forces, perhaps even a dark light, or a dark chemistry that dark matter particles use to interact with each other while remaining totally invisible to us. This opens up the possibility of a universe existing right alongside our own, a parallel world of dark atoms and dark molecules connected to us only through the long, slender thread of gravity. Knowing what to look for is one thing, building a trap for a ghost is another. The hunt for these particles has pushed human ingenuity to its absolute limits, forcing scientists to build some of the quietest, most sensitive experiments ever conceived in some of the most remote places on Earth. The main strategy used to hunt for WIMPs is called direct detection. The goal is to catch that 1 in a trillion event where a dark matter particle streaming through the Earth happens to bump into the nucleus of an atom in a detector. This bump would be incredibly gentle, causing the nucleus to recoil and release a microscopic flash of light or a tiny vibration. The challenge is noise. We are constantly bombarded by high-energy particles from space called cosmic rays. These particles slam into the atmosphere and the ground, creating a shower of secondary particles that would create a constant storm of false signals in a sensitive detector. To escape this cosmic noise, scientists must go deep underground. They have built their experiments in the deepest, most isolated places available inside active nickel mines in Canada, beneath a mountain in Italy, in a former gold mine in South Dakota, or under tons of ice at the South Pole. The miles of rock and earth above the detectors act as a massive shield, filtering out the cosmic rays and leaving the experiment in almost perfect silence, waiting patiently for the whisper, faint ping of a WIMP. These detectors are marvels of engineering. The Xenon NT experiment, for example, consists of a massive tank filled with nearly 9 tons of ultra-pure liquid xenon, one of the densest elements. The tank is surrounded by sensors that wait in total darkness for the tiny flash of light from a dark matter collision. And yet after decades of searching, building larger and more sensitive detectors, the result has been the same silence. We have not yet seen a definitive bump from a dark matter particle. This null result is in itself a profound and powerful scientific discovery. It has not disproven dark matter, the evidence from astronomy remains unshakable. But it has ruled out many of the simplest and most popular WIMP models. The WIMP miracle has begun to fade, forcing physicists to consider that the answer is more complex. Perhaps WIMPs are much lighter than we thought. Or perhaps they do not interact through the weak force at all. Or perhaps dark matter is not a WIMP, but something else entirely like the action. The hunt for actions requires a completely different kind of detector. Experiments like the action dark matter. Experiment ADMX do not try to catch a bump. Instead, they try to convert axions. Theory predicts that in the presence of an incredibly strong magnetic field, an axion can be transformed into a single particle of light, a photon. These experiments are essentially high-tech radios slowly tuning their powerful magnets through different frequencies, listening for the faint anomalous static that would signal the conversion of dark matter into light. This hunt too continues in the quiet dark. The persistent silence from these underground detectors has given new life to a radical minority-held idea. What if we are wrong about everything? What if there is no ghost particle? What if there is no missing mass? What if the problem is not with the matter in the universe, but with the rules? This is the central question of a theory known as MOND, or Modified Newtonian Dynamics. Proposed in the 1980s by physicist Mordechai Milgrom, MOND is a direct challenge to our understanding of gravity. The theory suggests that Isaac Newton's famous law of gravity, while perfect for our solar system and life on Earth, is incomplete. MOND posits that gravity itself behaves differently at very, very low levels of acceleration. At the accelerations we experience on Earth, Newton's law holds. But in the far-flung outer edges of a galaxy where the gravitational pull is thousands of millions of times weaker, MOND suggests that gravity does not fade away as quickly as Newton thought. It remains slightly stronger over long distances. If this were true, it would solve the galaxy rotation problem instantly. Vera Rubin's fast-moving stars would not be held in place by invisible matter. They would be held in place by this modified, stickier version of gravity. There would be no need for dark matter halos. The impossible dance of the galaxies would simply be the correct dance according to the true laws of gravity. For decades, MOND has been a successful underdog theory. It explains the rotation of galaxies in many cases better than dark matter models, but it has its own crippling problems. While MOND works beautifully for individual galaxies, it fails badly at larger scales. It cannot explain the gravitational lensing we see in massive galaxy clusters. Most importantly, it cannot explain the baby picture of the universe, the precise pattern of ripples in the cosmic microwave background. The CMB data is an incredibly strong pillar of evidence that the early universe did contain a massive component of non-atomic stuff, and MOND has no answer for this. This has led to even more speculative mind-bending ideas. Perhaps gravity is not just modified, perhaps it is leaking. Some theories, like string theory, propose the existence of more than the 3 spatial dimensions we experience. What if we live on a 3-dimensional membrane or brain, existing in a higher dimensional space? And what if gravity is the only force that can leak or reach between our brain and another parallel one? If that were the case, what we perceive as the gravitational pull of dark matter in our dimension might just be the very real gravity of normal matter existing in a parallel universe right next to our own, which we can feel but never ever see. We stand at a strange and profound moment in human history. We have used our ingenuity to look out into the cosmos and deep into the fabric of reality only to discover that we are the exception. The matter that makes up our bodies, our planet and our stars is nothing but a wisp of cosmic foam on the surface of a deep, dark and invisible ocean. We live our lives inside a ghost. We are suspended in an invisible scaffolding that dictated the birth of our galaxy, the formation of our sun and the very possibility of our existence. This scaffolding is the true architect of the universe. To know this is to feel a new kind of humility. It is to understand that the universe is not what it appears to be. The search for dark matter is not just a quest for a new particle in a physicist's detector. It is a quest to understand the fundamental nature of our reality, to finally see the invisible structure that holds us and everything we have ever known in its silent gravitational embrace. The fact that 95% of the cosmos remains a complete mystery is not a sign of our failure. It is the ultimate sign that the greatest age of discovery has only just begun. There is a famous idea, almost like a poem, that captures the heart of this new way of thinking. It says that the delicate flutter of a butterfly's wings in Brazil could weeks later set off a tornado in Texas. At first, this sounds impossible, like magic. How could something so tiny, so powerless, have any effect on something so massive and so far away? The air stirred by a butterfly's wing is less than a breath. It disappears almost instantly. Surely the great, powerful winds of the atmosphere would swallow that tiny disturbance without a second thought. For centuries, this was the assumption of science. We believed in a world of proportions. Big effects like a tornado must have big causes, like a massive cold front hitting a warm, moist air mass. Small things were just noise, tiny details that averaged out and could be safely ignored. This comfortable, proportional view of the world was shattered by accident in 1961. Not by a biologist studying butterflies, but by a meteorologist named Edward Lorenz. Lorenz was working at MIT using a very early room-sized computer to model the weather. His weather was a tiny simplified system governed by just 12 mathematical rules. He would type in a set of starting numbers representing things like temperature and wind speed, and the computer would print out a long sheet of paper showing how this weather would change over simulated days and weeks. One day he wanted to rerun a simulation he had done earlier. To save time, instead of starting from the very beginning, he decided to start in the middle. He looked at his old printout, found the numbers for the halfway point, and typed them back into the machine. Then he went to get a cup of coffee, letting the machine hum and clatter away. When he returned an hour later, he looked at the new printout and felt a jolt of confusion. The two simulations, the original one and the new one, should have been identical, but they weren't. They started out matching perfectly, but after a few simulated days, the new line on the graph began to pull away from the old one. By the end, the weather it predicted was completely wildly different. His first thought was that the expensive, delicate computer had a broken vacuum tube. He checked the machine. It was fine. Then he checked his numbers. This is where he found the butterfly. The computer's printout to save space rounded the numbers to 3 decimal places. For example, it printed 0.506. But inside the computer's memory, the actual number it was using was 0.506127. When Lorenz typed the number back in, he had used the shortened rounded number 0.506. The difference between the two numbers was tiny, less than 1 part in 1,000. It was a microscopic error, a difference so small it was like the weight of a single feather on a giant bridge or the flutter of a butterfly's wing. Lorenz had assumed, as any scientist would have, that such a tiny, insignificant difference in the starting point would only lead to a tiny, insignificant difference in the end. His model proved this assumption completely wrong. That tiny rounding error didn't just tweak the weather, it created a totally different weather system. This discovery was the birth of a new idea: sensitivity to initial conditions. This is the scientific name for the butterfly effect. It means that in certain systems, and it turns out, most of the interesting systems in the world are like this. Tiny, invisible, unmeasurable changes at the beginning can grow and be amplified over time, leading to massive, unpredictable differences in the outcome. Think of it this way: if you balance a single pin perfectly on its sharp point, what makes it fall? In a perfect world, it would never fall, but in the real world, the slight vibration from a truck driving by half a mile away or the tiny puff of air from you breathing is enough. That microscopic push is the initial condition. In the first millisecond, the direction it's leaning is invisible, but in 1 second, it is lying flat on the table, pointing in a direction left or right that was determined entirely by that one invisible push. Now imagine a system of 1 billion balanced pins all pushing on each other. This is the Earth's atmosphere. This sensitivity is precisely why long-term weather forecasting is and will likely always be impossible. It's not because our computers aren't fast enough or our models aren't smart enough. It's a fundamental limit of knowing. To predict the weather in 30 days, we would need to know the exact starting position, temperature, and momentum of every single molecule of air on the planet right now. We would need to know about every butterfly flapping its wings, every car driving down the road, heating the air with its engine, every ice crystal forming in a cloud. If our measurement of the temperature in Hanoi is off by just 0.001 degrees, that tiny error, as Lorenz showed, is enough to make a 30-day forecast for Paris completely meaningless. We can get better at 3-day or 5-day forecasts because the error hasn't had enough time to grow. But eventually the butterfly always wins. The tiny unknown details always take over. It is crucial to understand that this is not the same as pure randomness like rolling dice or flipping a coin. A coin flip is random. We truly cannot know the outcome. The weather is different. It is a system that follows very exact, very strict rules, the laws of physics like fluid dynamics and thermodynamics. If you could theoretically recreate the exact same starting conditions, the weather would unfold in the exact same way every single time. The system is deterministic, meaning it follows rules. The problem is that we can never know or recreate those starting conditions perfectly. The system is not random, but it is unpredictable due to its immense complexity and its sensitivity to the smallest possible change. This combination of deterministic rules creating unpredictable behavior is what scientists call chaos. For a long time, the word chaos just meant a complete mess, a total lack of order, like a room after a wild party. But this new science, which became known as chaos theory, showed something profound. Chaos is not just random disorder, it is a deeper, more complex kind of order. It is an order that is hidden, an order that is unpredictable but not patternless. When scientists like Lorenz began to map these chaotic systems, they didn't get a random spray of dots like static on a TV. Instead, they found beautiful, intricate and mesmerizing shapes. They found that even though the system's specific path was completely unpredictable from one moment to the next, its overall behavior was confined to a very specific, elegant pattern. This pattern is called an attractor. It's called that because no matter where the system starts, it will always be attracted to this particular shape. The famous shape that Lorenz's simple weather model traced was one of these. It looks like a figure 8, or perhaps more poetically like the 2 wings of a butterfly. This Lorenz attractor is a perfect picture of chaos. If you follow the line as it draws the pattern, you will see it loop around one wing, then suddenly swing across to loop around the other, then back again in a way that seems random. It weaves an infinitely complex pattern. The line will never cross itself, and it will never repeat the exact same loop twice ever. It is a portrait of orderly disorder, a system that is perfectly contained within a boundary, the butterfly shape, but is infinitely creative and unpredictable within that boundary. These mesmerizing fractal patterns were so new and unexpected that they were given an equally evocative name, strange attractors. Once scientists knew what to look for, they found this chaotic order everywhere. It's not just a mathematical curiosity, it's the very rhythm of life. A perfectly healthy heart does not beat like a metronome with a perfectly regular tick-tock tick. That is actually a sign of a sick or aging heart. A healthy, strong heart has a slight chaotic irregularity to its rhythm. This chaos is what gives it the flexibility to respond instantly and adapt to sudden needs like jumping out of a chair or running from danger. The chaos is a sign of health and resilience. You see it in the way a river branches into a delta, or the way lightning forks across the sky. You see it in the intricate patterns of a coastline or the structure of a snowflake. You see it in the seemingly erratic fluctuations of animal populations. A group of rabbits in a field doesn't just grow smoothly and then level off. Their numbers rise and fall in a complex, chaotic dance, driven by the equally chaotic systems of their food supply plants, their predators, foxes, and the weather. These are not random fluctuations, they are the result of a complex, orderly, chaotic system at work. This brings us to the most powerful and personal part of this idea: small causes can have enormous effects. This is the concept of non-linearity. A linear system is simple, predictable, and proportional. If you push a shopping cart with twice as much force, it moves twice as fast. The input matches the output. We spend most of our school years studying linear systems because they are the only ones simple enough to solve on paper. But the real world is almost never linear. The real world is non-linear. In a non-linear system, the effect is not proportional to the cause. You might push on a giant boulder a small cause and nothing happens. You push a little harder and nothing happens. You push just a tiny bit harder and you hit a tipping point. Suddenly the boulder lurches and rolls all the way down the mountain, a massive effect. The old saying, "the straw that broke the camel's back," is a perfect description of a non-linear tipping point. All the previous straws added weight linearly, but one final tiny straw caused a total non-linear collapse. Our ecosystems are built on these non-linear relationships. For decades, a lake can absorb pollution fertilizer chemicals and seem fine. Fishermen catch fish, the water looks clear. Then one more farm, one more small pipe adds just a little more pollution. This tiny increase pushes the lake over a tipping point. In a single season, a massive algae bloom can explode, turning the water green and toxic. The algae consumes all the oxygen and suddenly all the fish die. A small gradual change produces a sudden catastrophic collapse. The opposite is also true. For decades, Yellowstone National Park in the United States had no wolves. This absence meant the deer and elk populations exploded. They ate all the young trees and grasses, turning the river valleys into bare, eroded landscapes. Then in 1995, scientists reintroduced just a few wolf packs. This was a tiny cause, but it triggered a non-linear cascade. The wolves hunted some deer, but more importantly, they scared the deer away from the open river valleys. With the deer gone, the trees like aspen and willow grew back. With trees to eat, beavers returned. The beavers built dams which created new ponds. These ponds provided habitats for otters, fish and ducks. The trees stabilized the riverbanks so the rivers themselves stopped eroding and actually changed their course. The entire geography of the park was transformed, all from the wing beat of a few reintroduced wolves. And of course, this applies to our own lives. This is the web of chance. We are all living in a chaotic non-linear system. Think about the most important things in your life. Your job, your friends, your family, where you live. How did they happen? The answer is almost never a grand linear plan. It is almost always a story of small chance encounters and tiny, seemingly insignificant choices. You decide to go to one university instead of another. There in a class you almost didn't take, you sit next to someone who becomes your best friend. Years later, that friend introduces you to your future spouse. You miss your bus one morning. Annoyed, you stop for a coffee while waiting for the next one. In the coffee shop, you bump into a former colleague who tells you about a new company that's hiring. You apply for the job and it changes your entire career path. What if you hadn't missed the bus? What if you had chosen the other university? What if you had sat in a different chair? A tiny butterfly wing-sized change in your initial conditions would have sent your life down a completely different path. You would be a different person, living in a different place, knowing different people. This can be a frightening thought that our lives are so sensitive to random chance, but it can also be incredibly freeing. It means that the old view of the universe, the clockwork universe of scientists like Isaac Newton, is wrong. Newton believed the universe was a giant perfect machine like a clock. He believed that if you could just know the exact position and speed of every atom, every gear in the machine, you could predict the future with perfect accuracy forever. This was a deterministic and, in a way, a dead universe. It was a machine just running a program that was written at the beginning of time. Chaos theory tells us this is not true. The universe is not a rigid, predictable clock. It is something far more interesting and alive. It is more like a living, breathing body or a vast, dynamic, interconnected web. It is sensitive. It listens. A touch in one place can send ripples everywhere. The future is not a destination we are traveling to, but a place we are creating with every moment and every choice. This sensitivity means that the small things matter. It means that what you do right now counts. Your small, seemingly insignificant choices to be kind to a stranger, to learn a new skill, to speak up about an idea, to go to the coffee shop instead of the library, are all butterfly wings. We cannot know what tornadoes these small acts will create for good or for bad. We cannot predict the future. But we can know that we are part of this delicate, intricate and chaotic web. We are not just cogs in a machine. We are active, powerful participants in a universe that is constantly unfolding, a universe where everything, even the flutter of a single wing, can change the world. Our everyday experience gives us a powerful, comforting and deeply ingrained illusion that the world is smooth and continuous. When you look at a still lake, the surface appears to be a perfect, unbroken sheet. When you move your hand through the air, your motion feels fluid and uninterrupted. You can move from point A to point B, and in between there seems to be an infinite number of other points you can pass through. We can always in theory take a distance and divide it in half, and then divide that half in half again, and continue doing so forever. This is the classical view of space and time. We call this a continuum. This idea is the bedrock of much of our mathematics and our most successful physical theories, including Einstein's general theory of relativity. In that theory, space-time, the unified four-dimensional fabric of the cosmos, is a dynamic, flexible, smooth sheet. It can bend, stretch and ripple, but it has no seams, no gaps, and no fundamental smallest piece. But what happens if we challenge this intuition? What happens if we take this smooth image of reality and, like a digital photo, begin to zoom in? Think about a high-resolution photo on your computer screen. From a distance, it looks like a perfect continuous image, a face, a landscape, the galaxy. But as you zoom in closer and closer, the illusion shatters. The smooth curves break down. You begin to see tiny, jagged squares of solid color. You have found the pixels, the fundamental indivisible units that build the image. The image is not a continuum at all. It is a discrete, digitized system. The central question of modern physics is this: is our universe an analog photograph, or is it a digital one? If we could build a microscope powerful enough, a microscope that could zoom in past atoms, past the quarks inside protons, past anything we have ever seen, and zoom in on the fabric of space itself, what would we find? Would we continue to find smooth, unbroken geometry, divisible forever? Or would we at some truly mind-boggling scale of magnification suddenly see the pixels? This is not just a philosophical game. The answer to this question is the key to unifying the two great pillars of modern science. On one side, we have general relativity, the theory of the very large, which describes a smooth classical spacetime. On the other, we have quantum mechanics, the theory of the very small, which describes a world that is anything but smooth. Quantum mechanics tells us that energy is not continuous. It comes in discrete packets called quanta. An electron cannot have just any energy. It must occupy specific quantized energy levels. If energy is pixelated, why wouldn't space and time be as well? As we zoom in, we are probing the point where these two giant theories collide. We are asking what the atoms of space and the quanta of time look like. Our smooth continuous reality, it turns out, might be the most profound illusion of all. If we do zoom in all the way, we eventually hit a barrier. This isn't a physical wall, but a theoretical one, a scale at which our current understanding of physics simply stops making sense. This barrier is known as the Planck length. To say the Planck length is small is a galactic understatement. It is roughly 10 to the power of negative 35 meters. This number is so small that it's almost meaningless to our minds. Here is an analogy. If you were to measure a single atom and find its diameter, and then you were to measure the diameter of the entire observable universe, the ratio of the atom to the universe is still bigger than the ratio of the Planck length to the atom. The Planck length is the pixel of reality. It's not just very small. Many physicists believe it is the smallest possible distance that can be meaningfully measured, or perhaps that can even exist. You cannot have a distance that is half a Planck length, just as you cannot have a digital image that is made of half a pixel. This fundamental pixel is derived by combining three of the universe's most fundamental constants: the speed of light, the ultimate speed limit, the gravitational constant, the strength of gravity, and Planck's constant, the fundamental number that governs the quantum world. The fact that these three constants can be combined to produce a unit of length and also a unit of time. The Planck time is a profound hint that this scale is where gravity and quantum mechanics must finally unite. So what does a space's time look like at this Planck scale? It is not a static grid of pixels. Instead, the physicist John Wheeler, one of the great minds of the 20th century, described it with a powerful name: quantum foam. At this tiny fundamental level, reality is not calm and stable. It is a chaotic, bubbling, ferocious mess. The reason for this chaos is one of the central rules of the quantum world, the Heisenberg uncertainty principle. This principle states that you cannot simultaneously know certain pairs of properties perfectly. For example, the more you know about a particle's position, the less you can know about its momentum, its speed and direction, and vice versa. At the everyday level, this uncertainty is too small to notice, but at the Planck scale, the uncertainty principle goes wild. It no longer just applies to particles, it applies to space-time itself. It means that the space and time become fuzzy and uncertain. This uncertainty allows for a strange phenomenon: the borrowing of energy from the vacuum. The vacuum of space is not truly empty. At the quantum level, it is a roiling soup of potential. For incredibly short moments on the scale of Planck time, pairs of virtual particles can spontaneously pop into existence from literally nothing. A particle and its antiparticle using energy borrowed from the void. Almost immediately they find each other and annihilate, repaying the energy loan and vanishing back into nothingness. This isn't a theory, this effect has been measured in laboratories. It's called the Casimir effect. At the Planck scale, this process is so violent and so constant that space-time itself is torn apart and stitched back together. The foam, is a chaotic mess of these virtual particles creating tiny fleeting wormholes, microscopic black holes and bridges that connect different points in space and time. The smooth, stable, empty vacuum we perceive is just a long-term average of this underlying unimaginably violent quantum chaos. For the last century, physics has been built on two of the most successful theories in human history. They are the twin pillars that support our entire understanding of the cosmos. The problem is that in the most extreme places in the universe, these two pillars contradict each other. They cannot both be right. Pillar 1, general relativity. The theory of the very large. This is Albert Einstein's masterpiece. It describes gravity not as a pull between objects, but as the curvature of space-time. A massive object like the Sun warps the fabric of space-time around it, much like a bowling ball placed on a trampoline. Other objects like the Earth try to travel in a straight line, but they are forced to follow the curve created by the Sun. That curved path is what we call an orbit. General relativity is a classical theory. It is deterministic. If you know the present, you can perfectly predict the future, and most importantly, it describes space-time as a smooth, continuous fabric. It works perfectly for describing planets, stars, and galaxies. Pillar 2, quantum mechanics. The theory of the very small. This theory describes the other three forces of nature: electromagnetism, the strong nuclear force which holds atomic nuclei together, and the weak nuclear force which governs radioactive decay. It is the language of atoms, electrons, and photons. Unlike the smooth, certain world of relativity, the quantum world is lumpy, grainy, and probabilistic. Energy comes in discrete packets quanta. Particles do not have definite locations. They exist as probability clouds until they are measured. The very act of observing the system fundamentally changes it. The conflict. For most of the universe, these two theories live in separate houses. General relativity governs the large-scale stage spacetime, while quantum mechanics governs the tiny actors particles on that station. There is no conflict. The problem arises when the stage itself becomes tiny. The theories collide in places that are both incredibly massive, requiring general relativity, and incredibly small, requiring quantum mechanics. There are two primary examples: the Big Bang, the very beginning of our universe. According to our theories, the entire observable cosmos, all its matter and energy, was compressed into a point of zero size and infinite density. This is an infinitely small quantum and infinitely massive gravity object, the center of a black hole. When a massive star dies, it can collapse under its own gravity into a singularity, another theoretical point of zero volume and infinite density. When physicists try to apply the equations of both theories to these places, the mathematics breaks down. General relativity's equations, when pushed to zero size, produce infinities like dividing by zero. This is a mathematical error message. It's the theory screaming that it is outside its comfort zone. Quantum mechanics, on the other hand, says that you cannot have a point of zero size. The uncertainty principle implies that if you try to squeeze something into a point, its momentum and energy would become infinitely uncertain. Furthermore, the quantum foam from section 3.2 tells us that spacetime at that scale is not a smooth, simple point. It's a chaotic mess. This is the great conflict. General relativity demands a smooth, predictable singularity. Quantum mechanics insists on a fuzzy, chaotic, pixelated reality. We need a new theory, a deeper theory that can unite them. This undiscovered holy grail of physics is called a theory of quantum gravity. The search for a theory of quantum gravity is the single biggest challenge in theoretical physics. We have no direct experiments to guide us because the Planck scale is so impossibly small and high energy that we cannot reach it with any conceivable particle accelerator. All we have are mathematics, logic, and a few guiding principles. Out of this frontier of human thought, a few major candidates have emerged. The cosmic symphony string theory. Perhaps the most famous and most controversial idea is string theory. It proposes a simple, elegant, and radical solution to the particle problem. It says that if you could zoom in on an electron, a photon, or a quark, you would find it is not a point at all. Instead, it is a tiny, one-dimensional vibrating loop of energy, a string. The central idea is beautiful. Just as a single violin string can play many different musical notes by vibrating in different patterns, frequencies, these fundamental strings can also vibrate in different patterns. One specific vibration pattern appears to us as an electron. A different vibration pattern appears as a photon. Another pattern appears as a quark. All the different particles and forces we see in the universe are in this theory just different notes being played by these fundamental strings. The most exciting part of this theory is that one particular vibration pattern perfectly matches the properties of a hypothetical particle called the graviton, the quantum particle of gravity. In string theory, gravity is not a special addition. It emerges naturally from the music of the strings. However, string theory comes with a very strange price. For the mathematics to work without breaking the theory requires that the universe have extra dimensions of space, not just the 3 we know, length, width, depth, but 9 or 10 of them. The theory suggests these extra dimensions are compactified, curled up so tightly on the scale of the Planck length that we cannot see them. It's like a garden hose. From far away it looks like a one-dimensional line, but up close you realize it has a second dimension you can move around, the atomic fabric loop quantum gravity. This is the main rival to string theory, and it takes a completely different approach. Instead of starting with particles like strings and seeing gravity emerge, loop quantum gravity LQG starts with Einstein's general relativity spacetime as geometry and tries to quantize it directly. LQG takes the pixel idea literally. It says that space itself is not a smooth backdrop, it is a network. It is woven from a finite set of interlinked loops. Think of it like a piece of chainmail. From a distance, the chainmail looks like a smooth, flexible 2D fabric. But when you get close, you see it is actually made of discrete 1D individual metal rings. In LQG, these fundamental loops weave together to create spin networks, which are the atoms of space. These loops cannot be infinitely small. They have a minimum size related to the Planck length. You cannot have half a loop. This means space itself is granular. Time also flows in discrete ticks, not a smooth river. The beauty of this theory is that it directly solves the singularity problem. You cannot collapse matter to a point of zero volume because no such thing exists. There is a smallest possible volume. Instead of a Big Bang singularity, LQG suggests a big bounce, where a previous universe collapsed, hit the minimum possible size, and bounced back, forming our universe. It doesn't require extra dimensions, but it has a very hard time showing how our smooth, classical-looking spacetime emerges from this network of loops. The universe as a hologram. The holographic principle. This last idea is perhaps the most bizarre and mind-bending of all. It's less a full theory and more a principle that many physicists believe a final theory of quantum gravity must obey. We are all familiar with a hologram, a flat two-dimensional piece of plastic like on a credit card or passport that when light hits it can store and project a full three-dimensional image. The holographic principle suggests that our universe might be just like that. It suggests that all the information contained in our seemingly three-dimensional universe plus time is actually encoded on a flat two-dimensional surface at the very edge of the cosmos. This idea came from studying black holes. Jacob Bekenstein and Stephen Hawking discovered a shocking fact: the amount of information a black hole can hold, what fell into it, is not proportional to its three-dimensional volume as you would expect. It is proportional to its two-dimensional surface area, the event horizon. It's as if all the 3D stuff that falls in gets smeared and stored on the 2D surface. If this is true for black holes, why not the whole universe? This principle suggests that our 3D reality, including the force of gravity, might be an emergent illusion, a projection from a different, simpler set of quantum physics operating on a flat 2D boundary. We might be the 3D hologram projected from a 2D hard drive at the edge of reality. When we probe these ultimate questions, we eventually hit a wall. This is the edge of the map, the place marked "Here be dragons." In modern physics, this wall has a specific name: the singularity. A singularity is not a real physical place. It is a point in our mathematical theories where the equations break. It is a point where a physical quantity like density or space-time curvature is calculated to be infinite. As we discussed, our theories predict two places where singularities exist: at the center of every black hole and at the moment of the Big Bang. When our equations give us an answer of infinity, it is nature's polite way of telling us that our theory is wrong. It has been pushed beyond its limits and has failed. Einstein's general relativity, as beautiful as it is incomplete. A true theory of quantum gravity, like string theory or loop quantum gravity, is expected to fix these singularities. It would provide a new set of equations that work at the Planck scale. In these new theories, the quantum foam, or the atomic loops of space, would prevent a true collapse to a point of zero size. Density would become impossibly high, but not infinite. The singularity would be revealed as an illusion smoothed out by the fundamental graininess of reality. But even before we get to the singularity, black holes present us with another, perhaps even deeper mystery, the black hole information paradox. This is a profound contradiction identified by Stephen Hawking that tears at the very heart of physics. Here is the paradox, step by step, a core rule of quantum mechanics. Information can never be destroyed. It can be changed, scrambled, or hidden, but it is never truly lost. If you burn a book, you've scrambled the information, but in principle, a perfect physicist could gather every speck of ash and every particle of smoke and rerun the movie backward to reconstruct the original text. The information is conserved. This is a non-negotiable fundamental law. Hawking's discovery. In the 1970s, Stephen Hawking applied quantum mechanics to the edge of a black hole, the event horizon, and made a stunning discovery. Black holes are not truly black. Due to quantum effects, they slowly evaporate over trillions of years by emitting random low-level energy. This is now called Hawking radiation. The paradox. This radiation appears to be completely random thermal. It does not seem to contain any information about what fell into the black hole. If a black hole is formed from a star, or if it's formed from a library of books, the Hawking radiation it emits is identical. So what happens when the black hole completely evaporates and vanishes into a final puff of this random radiation? Where did the information about the books go? This creates a crisis. Did the information vanish forever? If so, then quantum mechanics is wrong and our understanding of reality is shattered. Is the information somehow hidden in the Hawking radiation in a way we can't see? If so, how? Does the information escape some other way, or is it stored on the 2D event horizon as the holographic principle suggests? This paradox has been the single greatest driver of quantum gravity research for decades. It is the ultimate stress test for any new theory. Solving it means reconciling the definite smooth geometry of gravity with the fuzzy information-preserving rules of the quantum world. 3.6. Contemplation to End, Part 3. Our journey into the fabric of reality has taken us far from the comfortable solid world of our senses. We began with the illusion of a smooth, continuous universe 3.1, a stage that we could measure and divide forever. But as we zoomed in, that smooth stage dissolved beneath our feet. We found a chaotic, bubbling and uncertain reality at the smallest possible scales, a quantum foam where space and time themselves are torn and remade every instant 3.2. We learnt that this grainy, uncertain quantum world is fundamentally at war, with our best theory of the large-scale smooth cosmos creating a great conflict at the heart of physics 3.3. This conflict forces us to the very edge of knowledge. To bridge the gap, we must entertain visions of reality that sound like science fiction. A universe where all particles are notes in a grand cosmic symphony played on tiny strings in extra dimensions. 3.4 string theory. A reality where space itself is an atomic fabric woven from indivisible loops, or perhaps most profoundly a world where our three-dimensional existence is merely a holographic projection of a simpler two-dimensional code. Our current maps of physics end at the singularities, the places where our mathematics breaks and our knowledge fails. These points, along with the deep paradox of lost information in black holes, are the sirens calling us toward a new, undiscovered theory. The final takeaway is this: the foundation of our reality is not the solid, stable, common-sense platform we assume it to be. The floor beneath your feet is not solid. It is the average behavior of an unimaginably large number of discrete probabilistic quantum events. The universe is not a static object, it is a dynamic, evolving process. It is not continuous, it is granular. It is not certain, it is probabilistic. The quest for quantum gravity is more than just a search for a final equation. It is a quest to understand the operating system of the cosmos, the fundamental pixels of our existence. The reality we inhabit is not just stranger than we imagine. It is perhaps stranger than we can imagine. The world we experience, the solid ground beneath our feet, the predictable cycle of seasons, the consistent warmth of the sun feels permanent. From the perspective of a single human life which lasts mere decades, the systems of Earth seem eternal. This perception, however, is an illusion. We are creatures of the now, and our senses are not built to perceive the vast, slow, and inevitable changes that operate on geological or cosmic timescales. When we stand at the edge of the ocean, it seems infinite and unchanging, yet we know that coastlines are constantly being redrawn. In the same way, the entire phenomenon of life on Earth is not a permanent fixture of the universe. It is a temporary, beautiful, and profoundly fragile exception. On the grand timeline of the cosmos, which stretches billions of years into the past and unfathomable trillions into the future, the tenure of life on this small blue planet is barely a flicker. The universe existed for more than 9 billion years before the Earth even formed. After our planet cooled, it took almost another billion years for the simplest, most basic forms of life to emerge. For more than 3 billion years, life remained a simple affair of single-celled organisms. The explosion of complex multicellular life, the kind we see in plants, animals and fungi, is a relatively recent development, a chapter that began only about 540 million years ago. If we were to compress the entire 4.5 billion year history of Earth into a single 24-hour day, the first simple cells would appear around 400 AM. The entire day would pass dominated by this simple life. It is not until 8:30 PM that the first complex sea creatures would evolve. The dinosaurs would rule the night from about 10:40 PM until 11:40 PM. The entire recorded history of Homo sapiens, all our civilizations, wars, art and empires would not begin until the final second before midnight. This deep time perspective is humbling. It reframes our existence. We are not the masters of a permanent kingdom. We are temporary tenants in a world that existed long before us and will continue long after us. The conditions that make our life possible are a delicate and fleeting convergence of factors. We require a precise distance from our star, a specific atmospheric composition, a stable magnetic field to shield us from radiation, and a narrow range of temperatures that allow liquid water to exist on the surface. This set of conditions is not static. The planet is changing, the sun is changing. The universe itself is a dynamic and often violent place. The horizon for life, therefore, is not infinite. It is finite. There is a definitive end. This section is an exploration of that end not as a single event, but as a series of inevitable processes and dangerous possibilities, a long twilight that has in many ways already begun. The story of life is a story with a beginning, a middle, and a definitive conclusion. Our planet's life is bound to the life of its star. The sun provides the energy that fuels photosynthesis, drives our climate and warms our world, making liquid water and thus life as we know it possible. But the sun is not a permanent, unchanging orb. It is a star, a massive nuclear furnace, and like all stars, it has a life cycle. It was born, it's currently in its stable middle age, and one day it will die. This stellar life cycle is the ultimate astronomical clock, and it dictates the final deadline for all life on Earth. The process that powers the sun is nuclear fusion, where it crushes hydrogen atoms in its core to form helium. This process releases a tremendous amount of energy. Over time, the helium ash builds up in the core, causing the core to contract and heat up. This in turn makes the outer layers of the sun burn even hotter and brighter. This process is slow, but it is relentless. Since its birth, the sun has gradually increased in luminosity. Right now, it is about 30% brighter than it was when life first formed on Earth. This slow brightening will continue. For every 110 million years that pass, the sun's energy output increases by about 1%. This may not sound like much, but over geological time, it is a definitive death sentence for our planet. As the sun's radiation intensifies, it will heat the Earth. This extra heat will cause more water to evaporate from the oceans, a process that is already beginning. The problem is that water vapor is a powerful greenhouse gas. Unlike carbon dioxide, which we can try to manage, we cannot stop the oceans from evaporating. As more water vapor fills the atmosphere, it traps more heat, which in turn causes more water to evaporate. This is a positive feedback loop known as a runaway greenhouse effect. In approximately 1 billion years, this process will reach a critical tipping point. The sun will be about 10% brighter than it is today. The average global temperature will rise to over 70 degrees Celsius. The atmosphere will become saturated with steam, and the oceans will begin to boil. They will steam away until the planet is completely dry scoured of all surface water. The immense pressure of the steam atmosphere will be broken down by solar radiation, with the light hydrogen atoms escaping into space. Earth will become a barren, superheated desert world much like Venus is today. Life, at least on the surface, will have been extinguished long before this final boilings, but this event will sterilize the planet completely, and the sun's evolution does not stop there. This is just the end of Earth's habitability. The end of the planet itself comes later. In about 5 billion years, the sun will finally exhaust the hydrogen fuel in its core. Its core will collapse, becoming incredibly hot, and it will begin to fuse hydrogen in a shell surrounding the core. This change will cause the sun's outer layers to expand dramatically. The sun will swell into a red giant. its size will become monstrous, ballooning out to potentially encompass the orbit of Mars. It will absolutely, without question, engulf and vaporize Mercury and Venus. Earth's fate is less certain, but equally bleak. It will either be swallowed whole by the sun's expanding atmosphere, or if it escapes being swallowed, it will be so close to the giant star's surface that its oceans will have long since boiled away, its atmosphere stripped, and its very surface rock will melt into a global ocean of magma. The red giant phase will last for a few million years before the sun finally puffs off its outer layers, leaving behind a small dense remnant called a white dwarf, the cooling corpse of a star. By then, the planet Earth will be nothing but a charred, lifeless cinder, or perhaps just a cloud of vaporized atoms within the dead star itself. Long before the sun's clock runs out, life must contend with a different, more immediate set of dangers. The universe is not a safe or quiet place. It is filled with random, violent events that can impact a planet without warning. Life on Earth has always been a participant in a dangerous cosmic lottery where the prize for losing is extinction. These threats can come from above, from below, or from deep space. The most famous threat comes from above. Our solar system is a busy place filled with the leftover debris from its formation, asteroids and comets. For the most part, these objects keep to their own orbits, but gravitational nudges can send them careening into the inner solar system. We have definitive proof of what happens when a large one strikes. 66 million years ago, an asteroid or comet estimated to be at least 10 kilometers wide struck the planet in what is now the Yucatan Peninsula. This event, which ended the 150 million year reign of the dinosaurs, was not just a large explosion. The impact itself would have been unimaginable, a force billions of times stronger than an atomic bomb, instantly vaporizing everything for hundreds of miles. But the real killer was the aftermath. The impact ejected trillions of tons of pulverized rock, soot and sulfur into the atmosphere. This dense cloud of debris spread around the globe, blocking out the sun for years, perhaps even decades. Photosynthesis on land and in the ocean stopped. The base of the food chain collapsed. Plants died, then the herbivores, then the carnivores. The planet was plunged into a deep, dark impact winter. This event shows that complex life is fragile. It is entirely dependent on a stable, uninterrupted supply of sunlight. We know this was not a unique event. Earth's pockmarked moon is a testament to the fact that impacts are a common recurring part of a planet's life. A similar threat can also come from below, from the Earth itself. The same tectonic forces that build mountains and shape continents also create massive underground chambers of magma. On rare occasions, these magma chambers can produce an eruption of a scale that dwarfs any volcano in human history. These are supervolcanoes. The last one to erupt on this scale was the Toba eruption in Indonesia about 74,000 years ago. When a supervolcano like the one at Yellowstone National Park erupts, it does not form a mountain. It blows a crater dozens of miles wide. It ejects thousands of cubic kilometers of ash and, more importantly, sulfur dioxide into the stratosphere, the high stable layer of the atmosphere. This sulfur gas forms a reflective haze that blocks sunlight, just like the soot from an asteroid impact. The Toba eruption is thought to have caused a volcanic winter that lasted 6 to 10 years, triggering a global cooling event and potentially reducing the early human population to a few thousand individuals, a near-extinction event for our own species. Finally, there are the threats from deep space. Our star is just one of billions in the Milky Way galaxy, and some of those stars die in spectacular fashion. A supernova is the colossal explosion of a massive star. If such an explosion were to occur relatively close to us within about 50 light years, the blast of radiation would be catastrophic. The initial wave of X-rays and gamma rays would be powerful enough to strip away Earth's protective ozone layer. Without the ozone layer, the planet's surface would be sterilized by the sun's own deadly ultraviolet radiation. Even more terrifying are gamma ray bursts, GRBs. These are thought to be the death throes of truly massive stars or colliding neutron stars. They are the most powerful explosions known in the universe, focusing their energy into two narrow lighthouse-like beams. If Earth were to be caught in one of these beams, even from thousands of light years away, the effects would be identical to a nearby supernova. Our atmosphere would be cooked, our ozone layer destroyed, and a mass extinction would be triggered. We would have no warning at all. One day a new bright star would appear in the sky, and days later the invisible wave of radiation would arrive, sealing our fate. These are the random, unavoidable risks of living in a dynamic and violent cosmos. For all of history, the greatest threats to life's existence have been external and non-sentient, the slow ticking of the solar clock, the random chance of an asteroid, the geological timetable of a volcano. But in the last century, a new and powerful force has emerged, one capable of altering the planet's fate on a timescale faster than any natural process. That force is humanity. We have for the first time created dangers that are a reflection of ourselves. We have built our own clock, and it is ticking much, much faster than the astronomical one. The most immediate and self-evident of these threats is the one we unlocked from the atom nuclear war. We have built an arsenal sufficient to destroy our civilization many times over. The danger of a full-scale nuclear exchange is not just the immediate death of millions in the initial fireballs. The greater planet-scale threat is the nuclear winter that would follow. The massive firestorms ignited in hundreds of cities would inject enormous quantities of black soot and smoke high into the stratosphere. This is the same mechanism as the asteroid impact. This soot, stable and high above the weather, would block a significant portion of sunlight from reaching the surface. Temperatures would plummet globally, even in the tropics. Agriculture would collapse worldwide. A war lasting only a few hours could trigger a global famine and ecological collapse lasting for a decade, potentially leading to the extinction of Homo sapiens. While nuclear winter represents a fast, catastrophic end, we have also engineered a slow-motion catastrophe. The slow erosion of our planet's life support systems through environmental collapse and climate change is a less sudden, but equally total threat. By burning fossil fuels, we have changed the chemical composition of our atmosphere, trapping heat and setting in motion that same greenhouse effect, albeit a slower version than the one the sun will one day inflict. This is causing ice caps to melt, sea levels to rise, and weather patterns to become more extreme and violent. This, combined with industrial pollution, deforestation and overfishing, is triggering the planet's sixth mass extinction. Biodiversity is not a luxury. It is the resilient complex web that supports all life, including our own. By weakening ecosystems, poisoning our water and warming the climate, we are slowly sawing off the branch we are sitting on. Our ingenuity has also given rise to new existential dangers. We have begun to create tools whose consequences we do not fully understand. One is uncontrolled artificial intelligence, AI. The threat is not necessarily one of evil robots as depicted in fiction. The danger is one of misaligned goals. We are racing to build a machine intelligence that is smarter than we are. A super-intelligent AI might be given a seemingly harmless goal, but it might pursue that goal with a single-minded inhuman logic, viewing human beings and the biosphere as either a resource or an obstacle. A machine that is vastly more intelligent than us would be as far beyond our control as we are beyond the control of an ant. Similarly, our mastery over biotechnology has given us the power to rewrite the code of life itself. While this has an incredible potential for good, it also opens the door to creating engineered pathogens. An accidental release from a lab or an intentional act of bioterrorism could unleash a virus with the lethality of Ebola, the transmissibility of measles, and a long incubation period. Such a pathogen could spread worldwide before it was even detected, creating a global pandemic that could dwarf any in history and bring civilization to its knees. Finally, these threats are compounded by our complete and total dependence on the fragile technological systems we have built. Our food, water, finance, communication, and energy all depend on global supply chains, the internet, and the electrical grid. This system is strong in its complexity, but incredibly brittle. A powerful, well-aimed cyber attack, or even a natural event like a massive solar flare, a Carrington event, could knock out our electrical grids and satellite systems. In a world plunged into darkness without communication, transportation, or the ability to pump water or refrigerate food, the intricate structure of modern society would collapse within days. We are a technological civilization, and we have forgotten how to survive without it. To be alive in this moment is to be standing between two great ticking clocks. The first is the cosmic clock. This clock is impersonal, vast, and utterly indifferent to our existence. Its mechanisms are the laws of physics, the fusion in the heart of the sun, the orbits of asteroids, and the life cycle of distant stars. It ticks in units of millions and billions of high quality. We cannot argue with this clock, we cannot negotiate with it, stop it or slow it down. It is the clock that will in 1 billion years boil our oceans. It is the clock that will in 5 billion years consume the planet in the fires of a red giant. It is the clock that randomly in the meantime might drop a rock on our heads or blast us with radiation from deep space. This clock teaches us humility. It defines the ultimate finite horizon. The second is the human clock. This clock is of our own making. It is loud, erratic, and ticks in units of years, months, and days. Its mechanisms are our own choices, our politics, our technologies, and our unresolved tribal conflicts. This is the clock of nuclear stockpiles of carbon dioxide emissions, of AI research, and of our dependence on a fragile grid. This clock is the reflection of our own nature, our brilliance and our self-destructive foolishness all mixed together. This clock teaches us responsibility. The profound and perhaps tragic reality of our time is that the human clock is ticking much, much faster than the cosmic clock. We are living in an impossibly narrow and precious sliver of time. We exist in a moment of profound fragility. We are balanced seemingly on a knife's edge. We have emerged from 4 billion years of evolution only to find ourselves possessing the intelligence to understand the universe, and in the very same moment the power to destroy ourselves completely. The present is not a stable state. It is a temporary clearing in the woods, a brief warm afternoon before the long twilight descends. The dangers ahead are immense. The paths to extinction are many while the path to survival is narrow. But contemplating this end should not be an exercise in despair. It should be a call to clarity. The cosmic threats, the suns aging the random asteroid, are beyond our control. We must accept them. But the human threats, the ones we invent and inflict upon ourselves, are entirely within our power to manage. The great challenge of our species is to diffuse the human clock. It is a race to see if we can develop wisdom, foresight, and a sense of shared fate before our own creations overwhelm us. We are the first species on this planet to become aware of the long cosmic twilight that awaits. We are also the only species that has built its own shorter twilight. The story of our future will be written in the tension between these two clocks. The end of life on Earth is a certainty, but the date and the cause is still for a very short and precious time in our hands. Our journey through the cosmos and the self has reached its end. We have travelled from the grandest scales of the universe to the most fundamental flickering components of reality, and now we must pause to ask what it all means. We began our search by looking out only to find that our world is defined by what we cannot see. We learned that we are shaped by invisible matter. Everything we have ever known, every star, every planet, every living creature is just a tiny fraction of the whole. Our reality is anchored by a vast unseen scaffold called dark matter, whose silent gravitational pull holds our galaxies together, preventing them from spinning apart into the void. Without this invisible shepherd, the structures that allow for our existence would never have formed. At the same time, our universe is being relentlessly pushed apart by an even more mysterious force, dark energy, a pressure built into the very fabric of space that accelerates the cosmos toward a cold, empty future. We are the visible foam on an ocean of profound, unseen immensity. From this cosmic mystery, we turned to our own history and discovered that our existence is not a grand design, but a staggering accident. We are governed by the most fragile chance. The emergence of this planet with the right ingredients at the right distance from the right kind of star was an improbable victory against astronomical odds. Life itself, sparked from inert chemicals, was another roll of the dice. Every step of our long evolutionary journey was a random turn, a fortunate mistake in the copying of our deoxyribonucleic acid, or DNA, a chance catastrophe like the asteroid that cleared the way for our ancestors. We are not the inevitable pinnacle of creation. We are an astonishing, beautiful what-if that against all probability just happened to become true. Our journey then took us inward to the very building blocks of our bodies, and we found that our foundations are not solid. We are built upon an unstable reality. At the smallest, most fundamental level, the world dissolves into a fog of possibilities. This is the strange realm of quantum mechanics, where a particle does not have a definite location until we try to find it. It exists in a superposition, a cloud of all the places it could be at once. The solid world we perceive is a grand illusion, an averaged-out consensus reached by countless flickering probabilistic events. The very act of observing reality changes it, meaning we are not passive witnesses, but active participants. We are not structures of stone, but temporary patterns built on the shifting sands of uncertainty. Finally, we looked at time itself and learned that our moment is finite. We are a brief flash of warmth and order of us in a universe that is steadily winding down. The cosmos is governed by a relentless, inescapable law known as entropy, which dictates that all things must move from order to disorder. Stars burn out, energy spreads thin, and complex structures inevitably break down. Life in its brilliance is a temporary rebellion against this flow. We are pockets of localized complex order taking in energy to build and think and feel, but this fight cannot last. We are a brief complex eddy in a great river that flows relentlessly toward a cold, quiet sea of equilibrium. We are a fleeting candle lit against an encroaching infinite darkness. So what are we? What is our place adrift in this ocean of invisible forces, born of pure chance, built on a foundation of quantum fog and living in a borrowed finite moment? The answer is as profound as it is simple. We are the universe becoming aware of itself. We are the cosmos's way of observing its own magnificent, terrifying, and utterly bizarre nature. We are the sensory organs of reality. Through our eyes, the universe sees the light of distant nebulas, light that has travelled for millions of years with no other purpose than to end its journey in our consciousness. Through our minds, the universe contemplates its own quantum weirdness, its own chaotic origins, and even its own eventual cold end. We are not separate from this chaos. We are the chaos organised just long enough to be able to name itself. Our awareness is the brief, precious window through which the totality of existence gets to have a single thought, a single feeling. We are the evidence that the universe is not just a collection of inert physical laws, but something capable of wonder. Our existence gives purpose to the silent swirling galaxies. We are the witnesses. This understanding changes everything. That simple ancient human act of looking up at the night sky is no longer just an act of passive observation. It becomes an act of profound self-reflection. When you stare into the darkness between the stars, you are no longer just looking out there. You are looking at the very substance that binds you, the invisible dark matter holding your own galaxy together. You are looking at the source of the elements that forge your being. The calcium in your bones and the iron in your blood were created in the fiery hearts of stars that exploded billions of years ago. You are quite literally made of stardust. When you trace the constellations, you are looking back in time, seeing light that is older than your species. You're also looking at your own destiny. You see the entropy and the dying embers of old stars and the vast expanding emptiness being driven by dark energy. The night sky is a mirror. It is our shared origin story and our collective final chapter written in light and gravity. It is the ultimate reminder that we are small, that our time is short, but that we are impossibly part of this grand cosmic tapestry. The universe we have explored is vast, complex, and deeply mysterious. It is far stranger than we ever imagined. It does not seem to have been built for us, but this is the crucial, beautiful, and final point in this moment. Against all of those odds, we exist. Right here on this small, wet planet, we are. We are the thinking, feeling, wondering part of it all. As this journey concludes, as you prepare for the quiet of sleep, let this truth settle over you. Feel the weight of the improbable reality that holds you. You're a collection of atoms that for a short while has woken up. You're connected to the farthest star and the smallest quantum particle. Feel the profound silence of the cosmos, but know that it's not empty. It is filled with the potential that created you. Feel that connection. Be at peace with the mystery. Good night.